Hello calculus students. Today we're going to continue integrating via substitutions. You remember you can also think of them with the Zen method. We're really going to focus on getting our substitutions written out right so that in the future we have a method to fall back on when we can't do one in our head. So I'd like you to try these first three integration problems first. Write out the substitutions, be real formal about it, and then you can check your answers after you've paused the video and worked them out. Alright, so let's go ahead and work these out. So, I need to pick a u-substitution. So, what do we think is the inside function here? I think on this first one, it's pretty easy for a warm-up. The inside that we're most presented with by the problem is that one. It's possible that that might not work though, so let's just see. Do I see the derivative of that lurking outside? I think it depends on your comfort with derivatives. Let's find out. So if I take du, then I'm going to take the derivative of 1, which goes away since it's a constant. This guy, I move the power down and decrease the exponent by 1. It is totally right there. That's x to the 1/2. So I could just write it like that just so I'm real clear. And of course I need my dx to preserve the notation. So let's see. I have dx and I have root x. That is equal to, if I solve, 2/3 du is root x dx. Okay, so this integral can become equivalently, those parts are 2/3 du, and then what we have is the sine, and we call that whole inside u. So that's a constant, so I can bring it out in front, so that's going to be 2/3 the integral of the sine of u du, and of course sine is just an integral we should know factually. So what is the integral of sine? If you're getting mixed up, remember, go back to one thing you're firm about. The derivative of sine is cosine, so that means the derivative of cosine is negative sine. So that means the integral of cosine is positive sine, so the integral of sine is negative cosine of u plus c. So this is negative 2/3 cosine of our u, 1 plus x to the 3/2, which I'm going to write like that. All right, there's our first warm-up problem completed. Let's look at another one. We'll do this one in red. So I think this one again presents a pretty common u, but you might want to think about this one a little more before you just jump into it. So I think u could be like maybe secant squared of that thing. It could be maybe secant squared by itself. Once you have experience, you should recognize that's not going to work. The most inner function is usually a good place to start. So I'm going to start with just cosine. So that means the derivative is negative sine of t dt. So is that lurking around outside? I think it is pretty much right there. I just need to divide that -1 to the other side, and it's right there. So this integral is equal to, those parts become negative du, and then we have secant squared of u, and remember this isn't minus du, it's times, so really I'm going to pull that minus right out in front right away. So now I just have negative integral of secant squared. So what is the integral of secant squared? If it's not jumping out at you, go back and look at your list of integrals. That's one we should have memorized, because the derivative of tangent is secant squared. So backwards, secant squared, the antiderivative, becomes tangent. But that's tangent of u, so I want the tangent of the cosine of t for my actual full-blown antiderivative. All right, let's do this last indefinite integral. Do this one in blue. So here I think the u is a lot less clear. This is more of a moderate level problem, and the kind that we really definitely want to build up to by the end of this lesson. So what could u be? U is a little bit trickier to decide. So it could be cosine. So we could try cosine. Let's try that. Of theta, right? Get my theta. Okay, so cosine of theta. So that means du would be, get my eraser. So that means du would be the derivative of cosine, which is negative sine. So if we made u this, is the derivative negative sine kind of lurking around out there? Well, the negative obviously is not, but there is a sine, but it's sine to the 5th power. So would I want to go like du to the 5th power? I I don't think we've ever seen an integral like that yet, and that's because, remember, the du is more kind of part of the notation. It's a helpful notation thing that's really important to keep track of for reasons like the key in our u substitution. But I don't think you can think about that notation being exponented or raised to the 5th power. So I think this was a bad choice of u, and as soon as you start trying to substitute it in, you're going to see that that's not going to work. So another choice of u you might try would be like sine to the 5th of theta. That would mean that du is bring the power down, right? Leave the inside alone. Oh, and then go power minus 1, and then you'd have to go chain rule, right? Derivative of the inside there is the derivative of sine, so that's cosine. Okay, so I see a cosine. I see a sine to the 4th. Let's try to write that one out. Let's see. So now I'm going to have better divide by 5, so I'll have du over 5. And then I have sine to the 4th and cosine, so that takes care of this and 4 of those. So far we have left one sine, because we took away 4 of them with this du over 5 thing right here, right? So we have one of those left, and now we have to deal with this, right? So how can we do that? The only way to go from there would be to, I think, figure out what sine of theta is. So that would mean you'd have to go like this on both sides. So that would mean the 5th root of u is equal to the sine of theta. So then I'd have this becoming the 5th root of u, which I think kind of works out there. But this is getting a little bit intense and mysterious, which some tougher integrals will tend to do. This, I think, worked out, but it was a little bit difficult. We had to go back and manipulate our key. There was a much better choice of u. We could definitely do this integral from here. Let's see if we get kind of the same answer, a much easier way, with a better choice. So I'm going to go back and start over. Try a better choice of u, because I think a lot of you at least would have gotten bogged down before you got to that final 5th root part. So let's try it a different way. My last choice of u that really is left is to make u the sine of theta. So that means that du would be what? So du derivative of sine is cosine. I totally have those parts right there. Good. So that means this is equivalent to so u is sine, so that's really just u 5th powered. So I've got u to the 5th power, and those parts are du. And that's a really easy integral, right? So that's going to be u to the 6th over 6 plus c. So that's going to be, what? The sine of theta, sine to the 6th of theta over 6 plus c. So you can see how easy it was to do that way. If you go back and work that other substitution down, I think you might be able to get it to come out to this. I'm not so sure that we didn't make a mistake either, so go back and look at that a little bit. But you can see that your choice of u can make things so much easier on yourself if you think a little bit flexibly. And also, the guiding principle of choosing u to be the inside worked again. If you think about this as the inside with notation, it's really just like those other two problems we just did. All right, let's look at a couple more before we wrap up this lesson. So just a couple more problems here. So for our last two problems today, I wanted to look at two definite integrals where we're finding the area under a curve from one spot to another. So yesterday in our first lesson, we looked at one way to do that, which was essentially to just find the antiderivative with your substitution, kind of ignore the equivalency, and then at the very end plug back in once you've plugged x back in and have an antiderivative in terms of x and not u. Another way to do that is to just directly make an equivalency at the beginning and just kind of change everything from x into u, or from whatever variable you have into u. So let me show you how to do it that way. It's important to kind of be flexible with this because the AP exam asks you to be flexible with it. And when you get to higher level calculus where you're doing multi-dimensional stuff, keeping track of what variable you're in, what dimension you're in becomes quite important. So let's have a look. I think this is a pretty easy substitution. You're probably already jumping out of the screen at me and telling me to make that u. If you did, well done. So that means du is 2x dx. We have our x dx right here. We just need to move this 2 to the other side of our substitution key. And then we can say that this is equivalent if we change everything into u, not just the parts inside, but also these. Because right now, these are also little mini x spots on that curve that we're supposed to find the area between. Okay, so let's go ahead and change everything. So far, u is this is u cubed. X dx together is du over 2. So we have x equals -3. What does that mean for u? Just use your key one more time. Remember, your key is there for your benefit. So if x is -3, just plug it into your key, and you'll see that u is -3 squared plus 1, which is of course 9 plus 1. So this is u equals 10. Or you can just leave that off and write 10, like most problems will in the future. But you can see it did not stay the same. You shouldn't expect it to stay the same because you changed the definition of your variables. All right, so if -3 is 10, what is 1? So I go over here and say, okay, 1 squared is 1, plus 1 is 2. All right, I'm going to move that work out of the way and finish the problem. So this says integrate 1/2 u cubed from 10 to 2. So that's going to be 1/2 u to the 4th over 4, evaluated at 10 and at 2. So that's going to be 1/8 b minus a, right? So I got to go 2 in. So that's going to be 2 to the 4th power minus 10 in. So 10 to the 4th power. And I'll get 1/8 of 16 minus 10,000. So that's going to be 1/8 of, what is that going to be? -9,984. So 1/8 of that, whatever it is, this is clearly a very large negative area. You'd have to look at the curve to see if that made sense logically. All right, let's do one last problem. So I'm adding, once again, you guys are kind of jumping out at the screen and suggesting a u substitution, hopefully. So I'm hoping that you would suggest this substitution to try first. Let's try it. So du, take the derivative, it's 2, constants go to 0, 2 dx. All right, so far we have, well, this part is u. Dx, just dx by itself is du over 2, just substituting in very directly, not mysteriously. And then so far we still have this x dude chilling. So did our substitution fail, or do we need to go back and use it again and manipulate it a little bit further? I think you can guess from the way that I said that we need to go back and manipulate it. This is a good substitution. I don't think there's a better one you can choose. If you think you can, I mean, go ahead and try u as the square root of that. I mean, that, or just making ux doesn't do anything. You could try u as the square root of that, though, and see if it leads you anywhere productive, but I don't think it's going to work. This will work. You just have to go up here and say, well, I need to get rid of that x. This defines what x is. It's actually u plus 1 divided by 2. That's what x is, so I can put that right here. I'm not going to use blue because all of this is now in terms of u. Now you might look at this like I did when I was a senior in calculus, and look at this and say, what's the big deal? They look equally complicated. In fact, this one even looks a little more complicated. But the initiated in algebra will look at that and say, I can chop that up and make it simpler. So hopefully you're seeing that a little bit. Here's what I mean. That is 1/2. That can be pulled outside. Just because there's more fraction garbage here doesn't matter. That's still 1/2 u plus 1 over square root of u. And I've got this 1/2 to also pull out, so that's really going to be 1/4. Okay? Now I'm hoping you can look at that based on what we've done this year, at least in my class, or anyone else watching this video, and simplify it by ripping apart the common denominator. So in this case, you can go u over the square root of u plus 1 over the square root of u, and those are easy, both easy integrals. Let me back up a little bit over here. So So we're going to say that's equal to 1/4 times the integral of u over root u. That's really just going to be 1/1/2. So that's really just 1/2. So that's really just 1/2. And that other one is -1/2 power. So that's going to be 1/4. Now we can finally perform our integration. So antiderivative of that guy is of course going to be add 1 and divide by 3/2, which becomes 2/3. And then we're also, I'm just going to put a parentheses here, so I'm not going to distribute the quarter this time, just a personal call. Plus add 1 and you get 1/2. If you divide by 1/2, that's the same thing as multiplying by 2. So that would be plus c. Remember, the last thing we wanted to do, just like this previous problem that was over here in blue, is we wanted to also avoid having to change it back to x ever. Sometimes that's more convenient, sometimes it's more of a hassle than it's worth, I think. You need to just be able to do it both ways. So these, remember, were both in terms of x, because the integral was in terms of x. So that means to make this actually equivalent, I have to put these in terms of u. All right? So I'm going to put 1 in. 2 times 1 minus 1 is 1. Coincidence. That's x equals 1 means u equals 1. Total coincidence. When I put 5 in, though, 5 in is 10 minus 1 is 9. So you can see that most of the time it's going to change. That is really coincidental right there. So I can clean this all up and make it equivalent by saying 1 to 9 for each limit of integration. So now I can evaluate this from 1 to 9, and I should be set. So let's do it over here. So we've got 1/4. We're going to go 2/3 times 9 to the 3/2. See, I'm going to try not to use my calculator on this one, because you can easily see this on the AP exam without a calculator. So 9 to the 3/2 is really the square root of 9 cubed. You can put that inside or outside if you remember from algebra. Plus 2 times 9 to the 1/2 is just the square root of 9. Okay, so that's f of b minus f of a. So 1's going to be much easier here. So 1 to any power is 1, so it's just going to be 2/3 times 1 is 2/3. And then 1 square rooted is 1, so it's going to be plus 2 times 1 is 2. All right, so we've got 1/4. Square root of 9 is 3, cubed is 27, so I have 2/3 of 27, plus 2 times 3 is 6. Oh, I shouldn't end that yet, right? That guy minus, and that's 2 and 2/3. Let's just put it all in thirds, shall we? So that's 6/3 and 2/3 is 8/3. All right, now I'm going to continue to simplify. 2/3 of 27, you could cancel it or do whatever you want. That's 18. So this is 1/4 of 18 plus 6. What's 18 and 6? I think that's 24 minus 8/3. So you could do this however you want. I'm just going to use a common denominator with a clever 1 to make it both be thirds. So that's going to be equal to 1/4 of, I might need my calculator. Now I think I'm good. 3 times 20 is 60. 3 times 4 is 12. That's 72/3 minus 8/3. So that's going to be 1/4 of 72 minus 8 is 64/3. And I think 4 goes into 64. 64 is in fact 4 cubed. Or you could go 4 divided by 64 is going to be 16. So that's going to be 16/3, I believe, for the area. You could always, of course, go back and check this integral with Math 9 and use the numerical integrator on your TI-84 or something else like that. But let's reiterate for the lesson. We need to be comfortable with selecting a u-substitution and learning to deal with the consequences of that substitution. Whether that leads us to something special like this moderate integral where we need to go back and use our key again, or whether we just need to start over and try a new u. Don't get intimidated. U-substitutions are definitely an essential for moving forward, and you want to be comfortable with them. And they will get easier if you practice and ask your teacher questions when you need to. All right, I'll see you next time.